Who here has heard of ZeroMQ? So this is not a new fundamental subject. Who here is programmed in ZeroMQ? Anyone? Well, that gives me my chasm, doesn't it? Okay.
Bueller?
I've heard tell. So I started with making some slides for the presentation, and then realized that I was basically making slides of the great ZeroMQ guide, and decided that I would just kind of scroll down the guide and talk to you guys about what's in it and skip some of the boring parts and point out exactly where in the guide you can go to look at how to make all this stuff work. Okay. So a quick overview of ZeroMQ and what it came from, or where ZeroMQ came from. A few years ago, a number of banks and software companies formed a bit of a coalition to create an open source messaging protocol. And they created AMQP. Now the guy that they hired to head up this, more or less, I'm not familiar with the exact contractual details as to his heading up of it, was named Peter Hinchins. Now, as you can imagine, what happened when you got a bunch of banks and large software companies together, the AMQP protocol that they developed could be described as bloated. And for whatever reasons, Peter was a little dissatisfied with the situation, without going into too much detail there, and decided to take a different approach towards writing a messaging protocol. And so he and a few others, particularly Martin Sustrick and another guy named Martin, I apologize, Martin, I just forgot your last name, and a few others got together and started making ZeroMQ. Now the whole idea behind ZeroMQ was to come through and say, let's not make a broker. I mean, AMQP and these AMQP guys, they're brokers. They're a different thing. Like RabbitMQ, ActiveMQ, and QPad. They're a daemon that sits somewhere in your network, and then you pass messages to it, and then that daemon ensures that those messages make it to their destination via some sort of messaging topology or protocol. ZeroMQ, on the other hand, cuts out the middleman, and if there's anything that car and furniture salesmen have taught us in the world, is that you save when you cut out the middleman. So that's fundamentally
Awesome.
That's fundamentally what ZeroMQ has done. And the benefit is that it is substantially faster than other message passing systems. It allows you to build message passing power directly into your application. And it allows you to do basically everything that these other guys, well, almost everything that these other guys can do, but do it much more cheaply inside of your code, and make your overall deployments much simpler. Fundamentally, it replaces writing network code with sockets, and now everything's faster, easier, and more awesome. If we scroll down, the way that they describe it involves a zip, pow, and a bang. Maybe I didn't need to scroll down. Nuts to that. But it is relatively magic how everything works. They go over TCP or UDP and just make sure the messages get passed from one place to another and do some fancy topologies. Okay. Now I had a slide that said, what can you do with ZeroMQ? There's a lot that you can do with ZeroMQ. ZeroMQ has built-in libraries for more than just your classic networking stuff, which is a client-server model, but allows you to do, it has built-in load balancing over multiple peers. It has built-in inter-process communication facilities. There's been a number of tests done that show that its inter-process communication is much faster than a lot of other programming languages built in inter-process communication. In particular, Python I'm going to talk more about Python because that's kind of my home turf for my examples. But for instance, Python in their multiprocessing class for all of their IPC uses pickles. And if you use, say, JSON or my preferred serialization method, which is message pack, then your IPC overhead goes down dramatically. And we're talking sometimes as much as 10, 20 times. ZeroMQ also has a PubSub mechanism. For those of you who aren't familiar with PubSub basically allows you to send a command out over the network in parallel to n number of subscribers. So you publish something out to a lot of guys at the same time, which is the fundamental way that the salt works. When I first looked at ZeroMQ and was reading through this guide, and I got down to PubSub, the light went on in my head, and I said, hey, that thing I've been trying to figure out how to do, I can do it now because of ZeroMQ PubSub. Okay. So we're going to walk through and talk about, actually I should stop. Does anybody have any questions at this point? Okay. I've either said everything that could possibly be said or you're not listening. Okay, so we're going to start out talking a little bit about how the most basic ZeroMQ topology works. And that's going to be a request-reply server, or in ZeroMQ vernacular, a rec-rep pair. So a rep server is a reply server, a rec interface is a request interface. And if we come down here to the very simple Python example, we can talk a little bit about how it works and what everything is doing. So, right off the bat, this is actually the client. These guys are punks. They don't have a server example in Python. I'm very glad that that statement has gone out across the internet because that means somebody other than me might write it.
Doubt it.
Okay. But the basic setup and usage of ZeroMQ, it's fairly straightforward. Make sure we've got access to ZeroMQ and Python. The dominant Python bindings for ZeroMQ are PyZMQ. They're made by the guys who make IPython. So regardless of your opinion of IPython, heck, they made it. They're not dumb. Okay, and then the next thing that you do is you make what's called a ZeroMQ context. This ZeroMQ context is the mechanism that builds all of our ZeroMQ sockets. And so we spin up a context and then make some sockets. So right here we say context.socket, and then we pass what type of socket this is going to be. As we go further into the different network topologies that we can use, we're going to run into a number of different types. So now we've got, yay, a socket. That socket can then connect or bind to an interface. Now, this is a request socket, so this is the client side of a rec-rep pair. If we're going to make the server, then it would be ZeroMQ.rep for a reply server as opposed to a request server. We would say socket.bind because we're going to bind to an existing port on the local system, and then tell it a TCP, localhost, or a local IP address, or a bunch of zeros, you know, to bind to all ports. Or sorry, to bind to all interfaces, not to all ports. You don't. Good gravy.
That'd be fun. I like that idea. 0 to 65, 535. All bound to ZeroMQ. What would Nmap look like on that? That's what I want to know.
It would probably take a while and be a very upset Nmap resolution. Anyway, and then bind it to a port. Okay. Then that socket has a send and a receive method. And you send data over a socket and you receive data over a socket. The manner in which this data is going to be sent, and the data is sent, it's always just a string. So there's no fanciness here. But that also means that if you've got a data structure or something like that, you're going to have to serialize that guy down to a string. And I'll find some niche in here to talk a little bit more about serialization and the considerations that you need to make when you're picking how to serialize your stuff. But in these early examples, we're just going to set a string. So we're just saying, hello. In this case, the client is sending it back to the server. The server would then do something with whatever the client has sent to it, and then reply. And then the client receives that reply by saying socket.receive. Now, in this case, when we say socket.send, it sends it off, it's non-blocking. Socket.receive is blocking. And so we just sit there and wait for a reply from the server. Now, one of the interesting things about ZeroMQ is that if we do socket.send and that server hasn't come up yet, the client can just kind of hang out and wait till it does, instead of just failing. So it can block until the server's up if you'd like. Similarly, when we do similarly, one of the nice things there is that you can restart a server, and if anybody was trying to connect to it while it was down, they were just hanging out till it came back anyway. So it's a relatively safe operation.
Is there a command for that? A different command for that?
A different command to make it not block? This does block.
To make it hang out and wait for the server.
Yeah, this is by default. It hangs out and waits for the server to come up. Okay. If we have time, I'll go into how to make it bail out if the server doesn't. If you're not getting a reply.
Like a timeout.
Yeah, there's what's called the ZeroMQ polling interface, or there's the ability to just fail if nothing's there and then try again later. Okay, but we do socket.receive when we receive the string that was sent back from the reply server, and we're done. Das ist alles. Oh, here's the zap, pow, boom. This is trying to explain that if you use ZeroMQ sockets, then magic happens in the background. My slide said that if you're using ZeroMQ, one of the things that it might do for you is that a watery tart might toss a sword at you. Come on.
It's not.
You're not getting the Monty Python reference.
Strange women lying in ponds, distributing
swords.
It's not a basis of programming language.
There's your dumb Monty Python joke. I get it.
Right. We can't have one of those. Yeah, you can't not do that. Now when we're talking about sending and receiving data, how ZeroMQ in the guide generally refers to data is by framing data, and they really like to express it in the construct of saying that we've got a string, and you should make your server assume that the first n number of characters in that string are going to be giving you a command of some sort or denoting the string. Now, I mean, that's a perfectly valid way of doing things. If you've got an application that's getting a little more complex, that has a more robust RPC going on, you might want to consider doing that differently. So as a reference, inside of Salt, for any of you who don't know, I'm the guy who wrote Salt, or spends all of his time writing Salt. So I will reference Salt many times. Okay, but yeah, so for instance, inside of Salt, we don't do that. Everything is purely serialized. We deserialize it and then determine what we want to do with that message. Okay. Now let's talk a little bit about a few more topologies and how they work. So a very common topology is the PubSub. So it's the same sort of thing that we were looking at before. You say context.socket. You tell it, we're not going to tell it ZMQ.rec. or rep, we're going to see ZeroMQ.pub, and then get back a publish socket, bind that somewhere, and then your clients are going to do context.socket, and then a ZeroMQ.sub to subscribe to a publisher. Okay? So they know that they're behaving in a different way. Now, how a publisher works is that you've got this one guy up here that's pushing data out. As soon as the subscriber connects to a publisher, it'll just start receiving information from that publisher. And as soon as it disconnects, it'll just stop receiving information from that publisher. There are a number of constructs that you can develop that allows the publisher to hang on to data, so much data, waiting for that guy to come back. And then when he comes back, he'll dump all that data to it. But that isn't turned on by default. That's actually a pretty important thing to be aware of, because ZeroMQ has a queuing mechanism. So every time you say send, then that ZeroMQ socket is going to hold on to that information locally and make sure that it gets over the wire. One of the major things that a lot of people complain about with ZeroMQ when they compare it to a full-blown AMQP broker is they say ZeroMQ isn't persistent. Because what a lot of these AMQP brokers do is they receive a message and then they write it to disk and then they forward it on to their destination so that it persists there. Now with ZeroMQ, you've got a cache and large. And you can either fill that cache up in RAM, or you can put a construct in there that writes it to disk for you, so you can get persistence. You just have to be aware of it instead of just hoping that that poor sysadmin who has to maintain your AMQP broker knows that if you send too many messages, it's going to bring down his server. Okay. So, PubSub differs. In RecRep, we have this two-way communication every time. You send the client says to the server, tell me about this. And the server replies and says, this is what you asked for. It's always two ways. A lot of ZeroMQ's topologies are purely one way, like PubSub. These subscribers, they don't have any callback mechanism. If you've got a server and it wants a callback mechanism from its subscribers, you're gonna need to set up a rep socket on there as well. Again, that's how Salt works. Is that a publication in Salt goes out to all of its minions, and then when they're done doing whatever they're doing with that publication, they connect back up to a different port on that master server that is the reply server to give them that reply and confirm that what they were told to do was done. But so this one-way communication kind of can trip people up sometimes. I've got some lovely background music going on here. It's rather soothing. All right, so let's look at how we set up a pub server. And you won't be surprised, but it's pretty much the same sauce over and over again. Most of understanding ZeroMQ is understanding how these interactions work so that you know how to group them together, how to make them work for you. So, we're importing ZeroMQ, we make a context. There's your boilerplate. That's your ZeroMQ boilerplate. We make a socket. In this case, it's a pub socket, as we can see. And then with that pub socket, we bind to all interfaces on port 5556 in this case. And then we start sending data out. And in this case, this is just going to keep shoving data out. God, with no sleeps in here, it's going to be doing it rather aggressively. Yeah.
So if it's shoving data out, but it's not really necessarily the PubSub method is not necessarily, there is no rec going back and forth to notify that yes, I'm receiving the transmission.
Okay, that's one thing that's interesting, is ZeroMQ takes care of that for you.
So-
See, there isn't a rep there, but ZeroMQ is doing
Some sort
any
of-
back and forth communication that it needs to validate that the pub makes it in its entirety, in its entirety,
So there's
down to the subscribing service. That's going on under the hood, so you don't need to worry about it.
okay.
So that you only need to deal with the high-level logical application end of the functionality.
Does it have the same buffering issue in regard to if there are any subscribers subscribing from the data, or does it just throw the data away after it submits it?
That depends on how you configure your publisher.
Okay.
Now, that lends us into another topic, which I'll inject.
Repeat these questions.
What was your question?
Does it cache on the publisher side?
Oh, the question was, does it cache publications on the publisher side? And yeah, the answer is that it can if you set it up to do it. Now, the way that you set it up to do it goes back into how these subscribers work. So we've got a pretty clear understanding of how a publisher works. It's the same sauce. We say context, socket, bind, send stuff out of said socket. Now, if we look down at how a subscriber works, very similar setup. Import ZeroMQ. We make a context, make a socket. This is a sub-socket because it's a subscriber. It's a connection. We're not binding to a port. We're connecting to a remote system. As we can see, well, in this case, it's localhost, so they're running on the same system. And that's the same port that we established up here, 5556. Okay? And then we go through here, and we're saying socket.receive, do stuff with that receive. This subscriber is only receiving a certain number of publications, and then it's just saying quit. Instead of being in a while loop. It's a for loop. Now, whenever we create a connecting socket inside of ZeroMQ, we can assign it something called an identity. So in the case that we're looking at right here, this is an anonymous socket. Okay?
The one name string.
So this socket right here, the one named, string is the data that we're getting back from the socket. String here is send here. Any questions on that? Okay. Because yeah, the receive method returns that which was sent without modification. Okay, so this socket right here, we're doing this guy. Bam. We're doing socket.setSocket option. So what we can do is slightly modify the behavior of a socket. And we can do this on a pub socket or on a sub socket, or rather a binding socket or a connecting socket. And so we're setting that ZeroMQ subscribes option is going to be set to filter, which is, where is that filter? Right there. So the filter functionality inside of a subsocket allows it to start receiving a couple of chars and then determine if it's going to, so if those chars match the filter, then we're going to keep downloading the rest of this publication. If not, then nuts to you. Okay? So it allows you to very quickly determine on your subscriber if that message is meant for the subscriber or not. Okay, but we can set a number of other socket options. And one of those socket options is ZeroMQ.identity. So if we set a ZeroMQ identity on a socket, and then it connects, and then it disconnects from the publisher, and then reconnects later, the publisher will save all of its publications that were never received by the guy with this identity, and then give them to that subscriber when it comes back online. Now, the thing that you kind of watch out for is that by default, there's no limit to how many of those it's going to save, which is why you'd come up here onto the socket that's binding and do a set socket opt ZeroMQ.hwm high watermark and say this is the limit to how many messages we're going to hang on to until we start dumping them for identified clients. And a high watermark works on a reprec server. It works on any of these guys. Okay?
So does it just register those identities when the client, when the subscriber connects to it? It's like if a new subscriber connects to it for the first time with an identity, then it basically says, all right, now you need to keep track of this identity.
Right. So the question is, when the subscriber gets a connection from a sub, is that when it builds a memory of that identity? And the answer is yes. As soon as that connection comes in, then the publisher builds something called the ZeroMQ infrastructure component for that subscriber.
What was the question?
The question was, when does the publisher remember the identity of the subscriber, or when does it become aware of it? Now, when that publisher is restarted, all that data goes away. But yeah, when a sub connects, that's when it remembers. It's also noteworthy in a PubSub situation that it remembers that by opening up a file descriptor. So if you've got a lot of subscribers, you might need to tell your system or tell that shell that it needs to accept more file descriptors. That was a problem we ran into with Salt when we got to the point where people were actually using it for more than about 500 minions, because they would report back that their masters were crashing because they didn't have enough file descriptors open. And so if you're running a Salt master with 10,000 minions, tell me, because I'd like to run some commands. I haven't gotten that high yet. But you'll need to change how many open file descriptors are allowed.
So what exactly is the fix? Changing the
So the fix, there's one of two things that can thank you, Clint, for bringing me this water.
I stole it earlier, so I would make up for
It's
it.
not one you've it's not the one you've drank out of
It's
already.
right there. Not bad. That mean.
Sorry, what was the question?
the fix?
The
For
fix.
the
Thank
PubSub,
you.
too
So
many-
if you're on a Linux
it's
system,
too many subscribers for one publisher, is that it?
no, it's not too many subscribers for one publisher. It's that the underlying systems by default have limits on how many open file descriptors you can have. Now, by default, a root shell on most Linux systems, for instance, has a limit of 1024 open file descriptors for any process inside of that shell.
So that's a problem on the server.
Right, and so you just need to change that with ulimit. If you're really, if you've got just an insane number of subscribers, you might need to actually change the allowable number of file descriptors that are available inside of your kernel. So you might have to hop into sysctl and go into procsys and modify that. I do not remember what that is off the top of my head.
Is there a way to tell, like, if you've reached your watermark? Is there a flag that goes off that says you started dumping because we were full?
Not that I'm aware of. The question was, is there a way to know that you've reached your high watermark on a ZeroMQ socket? And my answer is not that I'm aware of. I imagine there is, but I haven't particularly run into that problem. Okay, any more questions on how PubSub works? All right. Let's scroll down until we see whatever the next topology is in the guide, and I'll explain it. Okay. Now we get to talk a little bit about push-pull sockets. So, okay, we've talked about rep-rec, we've talked about pub-sub, and now we've got push-pull. I think we've only got router and dealer after this.
Yeah. I don't understand router.
Router dealer is awesome. But it took me a while to understand exactly what it was doing. Okay. So, push-pull. Now this topology here is a little more complicated than it needs to be. It's an example for push-pull. But nonetheless, push-pull is actually a really simple and straightforward setup. It's very similar in its architecture to PubSub in that it is one way. You push and it pulls and there's no reply. Okay? But so the difference with PubSub and push-pull is that say you've got a push server and it's got 100 pullers. And you do a push, you do a socket.send on that bound push socket. It's only going to go to one of the pull sockets. It's going to round robin through all those guys. Okay? So it's going to automatically load balance across multiple connectors. And that's fundamentally what push-pull is for. The other thing that push-pull is for is say that you've only got one guy and you've only got one interface that's going to be pushing commands out. Well, then that guy never has to respond with anything. Well, why have the overhead of responding? You should do just a push-pull. Okay.
What would that be useful for?
What would that be useful for?
That sort of round robin.
Anytime that you want to load balance processes. So it's let's say that you've got some sort of event system. Say you've got a big web tier, you know, some Ruby on Rails or some Django or some Bash on balls.
You just want to say all these funny things, don't you? That's your whole purpose tonight.
I try to put as many stupid comical points as possible. I know I'm not very funny.
Trick was get you admitted out loud, so.
Yeah, but it's been recorded. Don't worry, I will record many times that I'm not very funny and not very smart. All right, so let's say you've got a web tier out here, and they have events that need to go back to a tier of workers over here, but you've got to be able to assign them to the right workers. You've got to make sure that they're going to workers that are only on and responding properly, things of this nature. So you can have a ZeroMQ middleman in here that is probably a pull on this end, and these guys are all push. And this pull is backwards from this. This pull is a connect instead of a bind. Okay. Oh no, it's a bind instead of a connect. And all these pushes are connects. So they're all connected to this interface on this pull. And they're randomly sending information down to this guy. Okay. And it says, "Oop, I got something." And then it has, so it's got a pull on this end that is a bind. And then it says, okay, I've got a push on the other end that's also a bind socket, not a connect socket. And it says, I got a message, I'm just going to forward that on to my push to send out to my tier of workers. Okay? And so what you're able to do is have this choke point that allows a large tier here to communicate with a large tier of workers someplace else. Or as far as just having a one-way communication. Say you've got a local application, and it needs to do inter-process communication. And so you've got one process that's cranking along, and then it says, "Oh, I've got to push that off to a worker." And so you can have a bunch of workers that have pull sockets that are connected to a push socket that's a bind. So it's doing the sending, these guys are doing the receiving. And every time this guy's got an event, it says push this out, and this worker is going to do its business. And when it's done, it's done. I don't need to hear back from it. Okay? So let's look a little bit at the code here and see how they've got this set up. So they're starting with a push. And we bind that to a local port so that we can send out of it. And then they come in here, and we're going to make another socket that's a push, and it's a connect socket. So we see here that just because we have a socket type, it can be a connect or a bind. I think that the only socket type that cannot be a connect is a pub, and the only socket type that cannot be, I don't think a sub can be a bind. But other than that, they can all be bind or connect, and you can do everything forwards or backwards, however you've imagined forward to be. Okay, so we've got now a connected socket that's a push, connect socket that's a push, connect socket that's a bind. They're going to different places. Let's see. Man, do they have another one of these guys? Because those don't line up. There we go. Here's their receivers. Okay. Bound and connect. That means that the binding one is going to be sending information. So we've got this guy up here. This is a bind, because that's the direction the arrow is going for a push. It's pushing. And then we've got these pull guys down here, and they're in this block of code. And so they're all connects. These guys are connected up to this push interface. They do their work, and then they've got this pull interface. That's another bind, which is this sync right up here. And all of these pushes, which are now connecting to a pull and pushing that data, okay? So that they're able to say, jobs come in, jobs get figured out, jobs get pushed. Is that confusing enough?
So the pulls are kind of passive.
Yeah, the polls just wait for stuff to be pushed towards them. Any other questions? Arguments? Did I say anything that was horribly wrong sounding?
On the bottom, could you have more than one puller?
On the bottom, could you have more than one puller?
Like a whole array of pushers connected to an array of pullers?
Well, that would be fun. I'm trying to figure out what you do with that in tandem with figuring out how you would do it. The short answer is yes. The long answer is if you give me 10 minutes, I'll figure out how and why and all that stuff. You probably wouldn't be using push and pull if you were making a tree like that. Because in that case, you'd say that every one of these guys has 5 more guys that they're pushing to, so that there'd be more pullers. So it would be like this tier for each of these pushers, instead of having a cross-knit tier across multiple workers, because those can't, again, cross-communicate. So you would probably build a sub-tier out. But yes, fundamentally what you're asking is possible.
What if you had like a process that worked exactly like that? You had it working and you wanted to have, pushers just queued up, and you have no idea what kind of processes based upon the information you're going to have are going to be coming back in what order. Like there's 32 of them lined up, and how quickly they get finished with the task. Do you queue up like a bunch of pushers and like waiting for the pullers to check back in for the next task, or does that speed the process up, or?
So let me see if I'm interpreting your question
Right.
correctly.
I had a process that worked exactly like this at a job, and this would have been much more helpful.
I can't tell you how many times I've read this guide and thought about things in the past where I've gone, oh, I wish I had that food like 2 years ago. So correct me if I'm wrong, but I think that what you're asking is, let's say we've got a pusher. Jobs are coming in, and
jobs are there.
Yeah, jobs are there, and it pushes. It wants to push, but none of these guys are really listening because they're busy.
Yeah.
Right?
Right.
Okay. Then what happens is the push will say, okay, I'm going to present this message. And one of these pullers is going to take it. And if nobody takes it, it goes in a queue and just waits until a puller is ready to accept that, or until it hits the high water mark and it starts throwing them away.
That's the question. There is a high water mark. Okay.
Right.
Okay.
And we do that with ZeroMQ.setSocketOpt.
Okay.
Okay.
That would be so much easier.
Let's see. So here we've got just half of that again. I think I already explained this component where you've got multiple pushers and one puller. And again, the fact that a push can connect or bind, a pull can connect or bind, a rep can connect or bind, and a rec can connect or bind. All right.
Dealers.
How much time have I
Brokers and
consumed?
dealers.
Yeah, I'm just going to scroll down. My whole plan is to scroll until we get to one of these topologies. And once we get to the bottom, and I've talked about all the topologies that are in here, because I'm really just looking for router dealer. Okay. Well, they've got pairs now. I used to feel all cool because Salt was using everything, and then they made pairs. Okay. Now, ZeroMQ, technically, you could probably connect a bunch of pullers to a pub socket, but they're not going to guarantee it's going to work. Okay? If you can imagine how that would work. But so generally, when you're setting up all of these topologies, you need to pair them with the right guys. And we've already talked primarily about this. And that's pub and sub are the compatible guys. Rep and rec are compatible. Rec and router are compatible. Dealer and rep, dealer and router, dealer, router and router. And push and pull, and pair. But yeah, you can, if you connect them to other ones, they might appear to work for a little while and do some crazy thing. But, if you ask a question about it on the mailing list, well, those are fun. Or rather funny as an observer. Okay. Come on, where's the router dealer? Ooh. Here we go. We'll do this. Now, the nice thing that's going on here is that we're starting to combine multiple pub-sub situations. And I was going to say, if there's a dry erase marker later on, I might make use of said board over there. But so,
It's even got ZeroMQ.
it's even got ZeroMQ stuff on there already. And before we leave, I have to like circle message pack, cross out pickle, and put something under JSON like, you want to deal with binary encoding? Really? Okay. So, what we're looking at here is that we've been able to combine functionality to get more of a result that we want. Because we've got the same push-pull worker setup, but now back here on the sync end, it's able to say, we've processed all the work we need to process, so I've got a pub, and all of my worker systems, whether they're threads, processes, servers, whatever, have a sub back to my pub. And in this example, they're saying, okay, we've queued up so much work. When that work is done, kill all of these workers. Because the idea in this setup is that, okay, instead of sending a single command through this ongoing pipe, what's going to happen is we're going to have these groups of jobs. When a group of jobs comes in, we're going to say, aha, we have a group of n jobs. Spin up n workers and put them to work. Oh, the jobs are done. Kill the workers. Okay?
What are you, the Pharaoh?
I know, that's what I was thinking. That's exactly what I was thinking.
No, I'm a Unix and Linux guy, and when things are done, you kill them. I would also prefer to be Vlad the Impaler instead of a pharaoh. Okay, but you get the idea. And so we make a few minor modifications to how we're managing these interfaces, and the result is that we can easily mold this earlier topology to a relatively different task. And frankly, this is pretty straightforward, because all we've done here is added a pub sub. And we looked at those. They're not too particularly complicated, are they? Okay. Now, they're going to do a bunch of these silliness, aren't they? You can build a tier. Basically, if you can imagine it, ZeroMQ can transport layer it. Okay. There we go. Now we're talking. Next, we've got this router dealer construct. This is the last topology construct I'm going to talk about, and then I'm almost done, actually. And then I'm going to talk a little bit about serialization options and what to choose and how to pick a serialization method. And then I'll tell you just to use MessagePack because it's awesome. And that if you honestly think that you should use YAML to serialize network data, then you should be shot. Okay, now, router dealer. How a router dealer works is that, let's say that we've got 50 servers or interfaces out there, and they're all going to be wanting data. So it's kind of like a website. They all want data from an Apache server, right? And as that comes into Apache, Apache says, oh, you want me to give you data? I'm going to hand that off to one of my worker processes, and then that worker process is going to give you the reply, right? Effectively, without us going too deep into Apache. So we can do this same thing with ZeroMQ. And those workers don't necessarily have to be processes on a system. You can span those out to be a full round-robin tier of worker servers in the background. And those guys could have a router dealer setup that does have processes on it. So it can be stretched to the length of your imagination. Okay, so you've got a router. It's going to act kind of, in this scenario, it's going to act kind of like one of those rep servers. Okay, so a request server is going to bind to it and say, hey, tell me something about this stuff I sent you. Instead of this guy just responding, it's going to say, okay, I'm going to hand that message off to a dealer. And then that dealer is going to forward that message on to a reply server. I'm going to remember how this message has been routed so that when this reply server replies, I know to send it back to the guy who originally requested it. Okay? Does that make sense at all? Or should I say it again?
Sure.
Or should I try and say it differently?
No.
Okay.
They're proxies.
Yeah, they're proxies, they're natting, they're routers. Okay. If you look at some really old, I shouldn't say really old, some older, as in like 6 months ago, ZeroMQ code, routers and dealers were often referred to with XREP and XREC. So if you see that, those are actually completely interchangeable with router dealer.
As in transmitter.
Yeah.
Okay.
Yeah, as in transmitter.
Okay.
All right. Now let's take a little quick look here. Where's their code start? At their code. Okay. So normal boilerplate. We're making a rec socket. We're connecting it to something. Okay, and we say, oh, we're going to receive. We come down to the next one. We're making a reply socket. We're connecting it. We receive. And here's where things get kind of interesting. Is with our router and dealer. So we're calling it front end in here. We're creating a router type socket. And then we're creating a dealer type socket. They're both going to bind to local ports. Okay. They're making a poller, which is going to allow you to poll for data in a way that doesn't always block. So this goes into one of the ways that we can not have our sockets blocking. Okay. And so this guy comes in and it says, okay, message receive. It can do a receive more, which I'll explain in a minute. Okay, so it receives it, and then it hands it off to let's see, and then it should be handing it off to the back end there and forwarding it on. Now, the way I have implemented this in the past is using something called a ZeroMQ device. A ZeroMQ device is kind of like this right here. It allows you to say that I'm going to make a local Unix socket or an IPC interface, and I've got a bunch of workers. They're going to connect to this device, and that's going to be my routing mechanism. But fundamentally, this is the flow of a router and dealer. Now, there's a couple more things that I want to talk about before I go into serialization, as long as you guys aren't bored completely stiff. Okay. Oh.
Good timing.
A tape change. Allow me to spit off a string of vulgarities.
Do it. I want to see it happen.
Yeah, which string would that
No,
be?
you know me.
I do know you. That's why I
Yeah,
want to
it's
see
not
it
gonna
happen.
happen. Tape or no tape.
It'd be awesome.
That's great. If I ever need
So-
to use one of those, you'll know I'm serious. Yeah.
I don't know if it's a question worthy to be on tape, but explain to me the router method and the dealer method and why they'd ever be used.
Why'd that ever be used?
Yeah.
So the question being, why would we ever use a router and dealer?
No. No. The combination pairs allow you to use like router and router. I mean, right? I mean, as I understand them.
Well, the router is kind of the input and the dealer's the output.
Right.
So,
Or have I misunderstood all that?
So what would you do with the dealer?
That'd be fun. It's like play cards.
I mean, isn't it, according to the documentation, it's a valid combination pair.
exactly. Now let me give you an answer that's kind of going to be a cop out. I haven't spent the 15 minutes thinking about that.
Okay.
It's one of those things where, yeah, sit down and go through these. Once you figure out a topology, go, what can I put those together? And you'll come up with something. If I were to go back up to all of these pairs, I could say, I've really only sat down and thought about maybe 2/3 of these and how I would use them. But yeah, go on. See, there's plenty of really cool stuff that you could do with a dealer and a router. Make it really just kind of web out into some sort of madness.
Everybody likes the madness.
Generally, this is the scenario that I've seen people use, and that I've seen people present, is that we're going to spin up a bunch of workers with a persistent connection back, as opposed to like those push-pull workers, and they didn't have a persistent connection back. What were the other constructs that I wanted to go over with you guys? Because I just said them, and they came to my mind while
Serialization.
in here. Okay, we've got serialization, we've got receive more and send more. Now, receive more and send more, that's kind of interesting. The first time I wrote a file server with ZeroMQ, and as just a rec rep pair for the file server, I used receive more and send more, because in my initial readings of them, it sounded like it meant that I could say send so much and then send some more. And they came back and said, okay, yes, it does send so much and then send some more. But it does load everything into RAM. And I thought, that's not what I want for a file server. So I designed it a little differently. But basically, the idea with send more and receive more is that we can say, okay, we have prepared a message of n length. And I'm going to send some of that message and then make a determination about the contents of that message and see if it has a receive more on it. And then if it does have a receive more associated with this initial message, then I'm going, and I want the rest of it. And then I'll tell it, yeah, give me the rest. Or I'll just go, nah, I'm not going to do anything with it, so don't give it to me. Okay? Make sense? All right. The next thing to look over is serialization. Now, serialization has a long and wonderful history. Got some chuckles. The basic construct of serialization is to take a data structure and turn it into something that is portable in a string, and then send it along and send it someplace else. And then you get to decide how you want to use that portability. If that portability means it's going to port over a network or something, right? I mean, we can go back all the way to like bare encoding in ASN1 and talk about how that is used as a serialization methodology. But modern serialization, there's been kind of a war over the last few years because XML came out, and a lot of people thought that XML should be used for a lot of things that it probably never should have been used for. And
I know, I was thinking so.
sorry, what were we thinking? So someone was thinking so. And so a lot of the original RPC work that I did was using XML RPC. And I look back at that and think, wow, what a wonderfully bloated way to serialize our data for network traffic. No wonder I sent everything through gzip before sending it on the wire. So there's a lot of serialization mediums out there today. I'm going to say kind of flat out that you should not use Python pickles. Python pickles are, granted, they're very convenient. Granted, Python pickles are pretty quick as far as comparing them to something like, well, serializing with XML. But there's a lot of better ways that you can do it. Pickle isn't very portable, so if you use Pickle as your serialization layer for a network protocol, then you have bound yourself to Python forever, which there are worse things. The other thing that's probably more important with a Pickle is that if you ever use Pickle for network serialization, you've got to keep in mind that whoever deserializes that Pickle is going to be executing Python code. So if anybody compromises one of those, they can inject anything into a Pickle, and it'll be deserialized without discretion on the other end, which means that you can get complete pwnage of a box by putting an os.system inside of a Pickle that puts your root SSH authorized key in there, or something like that. Okay? So I'm going to discourage Pickle use. The next serialization medium that everybody thinks about usually is JSON, because we use a lot of JSON. And frankly, JSON is a incredibly awesome thing. And what happens is JSON is well, with the benchmarks I've done in Python with serializing, JSON 1, it limits you to what most serialization mediums limit you to. And that is dictionaries or hash maps, or depending on what your programming language of choice is, however you want to call these things. But dictionaries, hash maps, construct, lists, strings, and ints, or numbers. Okay? And that's pretty normal when you look at serialization. The main benefit when using something like a Pickle is that you can use a Python object. Okay. But so JSON generally, in the benchmarks I've done, is a little quicker than a Pickle for serialization, but not much quicker. Okay? It is very portable, but if you're putting a lot of binary data into a into a JSON string, you're going to have to do a little extra work. And it doesn't always like those. Okay? But apart from that, it doesn't have very many limitations, and it's a pretty good serialization medium. Now, some other serialization mediums out there are protocol buffers, which Google put together. They're powerful, they're fast, they're very efficient, and a lot of people are really excited about protocol buffers. And I'm not going to discourage you from using protocol buffers. It's good stuff. If you're going down your list of serialization mediums and protocol buffers offers you some benefits for what you're looking at, then it's good. It's good stuff. Now, there's a couple others that are extremely simplified serialization mediums. And there's some binary serialization mediums that are worth mentioning. Now, there's BSON. Some people are very excited about BSON, and then again, a lot of people are very excited about what BSON was made for, and that's Mongo. The problem with BSON is that the only real BSON implementations out there, well, last I checked, about a month ago, are clients for Mongo. So you might run into that problem. Other than that, BSON is very fast, very efficient, and allows you to do some more complicated constructs because it allows you to build things in more of a Mongo-esque fashion. If you need to push beyond just having dictionaries, lists, strings, and integers, that's when you start looking at things like protocol buffers or BSON. the problem, of course, with BSON, again, you're going to have to find somebody who's written a BSON serializer and deserializer for you, or be willing to go through spec and write yourself. Now, the next one to consider is called T-net strings. T-net strings were developed for Mongrel 2. So if you ever have any problems, you might have to deal with ZSHA. But T-net strings are really smart because they're a plain text serialization medium. All they do is put certain characters in front of a group of text to tell that group of text what it's going to be, which means that it's very compact and it's also really fast. Okay? So T-net strings are some pretty cool things to use and very, very simple. Now, they're again, it's not the kind of thing that you're going to find a library for. It's the kind of thing that you find a specification for. And you're informed that, okay, here's a specification for net strings, now write it into your application. Now, after going through all these things, my serialization medium of choice is called MessagePack. Now, the goals of MessagePack were to make a serialization medium, and they come with a little RPC API too, if you want to use it, that you can use. The basic downloads of MessagePack don't include it, which is also nice. MessagePack is incredibly compact. The Python implementation of MessagePack, for instance, is written in Python, so it compiles down to C, and so it's ridiculously fast. MessagePack uses a very similar construct to T-net strings. So it's using, but it's binary. So it puts binary data inside of your strings so that you can determine where your cutoffs are. Okay? And there are implementations out there for pretty much every programming language, even like OCaml. And then
You don't know what camel is?
you know, somebody doesn't know what OCaml is? OCaml is pretty cool. It's kind of like taking the ML functional programming idea and then doing to it what C++ did to C. Now, some Frenchman who, because it's French, OCaml is going to hang me for that. I think OCaml is really cool stuff. It's a fun programming language. But anyway, you've already got it implemented in all these different languages for you. And it is ridiculously fast. So, I originally, naively, when I made Salt, used Python pickles as my serialization medium for all my message passing. And then, a little later on, discovered that I was a fool because of massive security issues. So please do not install Salt 0.8.7 or one of those old ones. I don't know why you would anyway. But, so I went out and I did an investigation of all of these different serialization mediums. And I put together some scripts that would serialize some very different data. Because I found out that some guys, you know, they may be able to handle some big strings that are binary strings really well, and they don't bat an eye. Whereas other serialization mediums get bogged down on those sorts of things. And some guys, if you give them a ridiculously complicated data structure, they will take forever to deal with that data structure. So what it boiled down to was, I was always testing against Python pickles. They were kind of my benchmark. And then I used JSON and protocol buffers. I didn't get around to using BSON. Then I used MessagePack and ran a number of these tests. I started with pickle and got some benchmark numbers. Went through JSON and discovered that it was just a little bit quicker than pickle, not enough to really, you know, raise an eyebrow. protocol buffers were a lot faster, a lot more efficient. They were also a lot more efficient size-wise. Pickles they get kind of big. And I was looking at that going, oh, protocol buffers look very promising. And then I wrote the code in MessagePack, and I got to admit, my initial impression of MessagePack was that these guys looked like a bunch of kids in a basement, and Google made protocol buffers, so it should probably be pretty well made. But so I ran MessagePack, and one of these tests was taking on average about 10 seconds using a Python pickle. It was about 4 seconds using protocol buffers. It was something like 9.5 seconds in JSON, and then I ran this test in MessagePack, and it did it in 0.08 seconds. And the data that it output was less than a third the size of the pickle and less than half the size of JSON and protocol buffers. And I figured that I was good. And ran through all the other tests, and they all had the same result. Massive benefit with MessagePack. So then I implemented it inside of Salt, and told Salt to do some of the heaviest things that it can possibly do over many, many minions. And the result was that all of a sudden, all of my Salt operations had almost tripled in speed because of a switch to MessagePack. So that's my overview of serialization mediums that I've actually played with. All right. We've gone over a lot of this stuff. Like I said, I'm embarrassed. I don't know pair very well yet. Does anybody have any questions, arguments, comments, pitchforks?
What other protocols might this use? I saw that it used TCP in there.
Oh, that's something else I should have talked about, is what other protocols you can use with ZeroMQ. Now, TCP is normally what you're going to use over the network. It takes care of a lot of the work for you. It's a good way to go. The other protocol that is probably, let's see, there's two others that are probably worth mentioning. There's InProc. InProc is a protocol that does everything in between threads. So you can have a bunch of threads that are intercommunicating using InProc. The next one that's noteworthy is IPC. And IPC means that you're going to be binding to a Unix socket. This is actually, I mean, some of the first ZeroMQ code I wrote, I had no idea about InProc and IPC, and I wrote all of my workers to be connecting to inwardly bound ports over TCP, and needless to say, things got a lot quicker when I started switching over to Unix sockets. But yeah, IPC allows you to connect via Unix sockets. I think they didn't last I checked, and if they ever do, then they'll get my Saltmaster running on Windows. But I think that they have developed an IPC system that works on Windows as well, so that you don't need the glory that is Unix sockets. And an InProc, again, that's something to just be aware of. The InProc protocol is actually, if I'm not mistaken, it's used in the background anyway between ZeroMQ threads. One thing that's really keen about ZeroMQ is that it'll spin up threads for you in the background, and it operates outside of interpreted languages, thread locking mechanisms, aka ZeroMQ backend threads don't need to adhere to the GIL, which is very keen. But ZeroMQ takes care of all that threading magic for you in the back. But basically, TCP, InProc, IPC. There's another one that I haven't used called PGM. And I'm trying to remember what it does, but it's not coming to my memory. But yeah, for the vast majority of what you're doing, it's going to be TCP or InProc or IPC. Is that a satisfactory answer?
Sure.
Okay.
You're talking about this simplifies your deployment. Like, how is the install? Or how do you get it started?
So getting going with ZeroMQ, you've got a couple of options.
Repeat the question.
The question was how do you get ZeroMQ installed and how do you get going with it? And is that a big deal? Now, ZeroMQ itself is written in C++. And so if you want to be binding to it via C++ or just want to raw bind to ZeroMQ, you just need to install ZeroMQ. ZeroMQ is just a make install, so /configure make install. Or many Linux distributions out there have packages for it. We had to get some of those packages in so that we could get salt packaged. But yeah, that's a pretty straightforward process. And yeah, so if you're running like Fedora 16, you can yum install ZeroMQ. You've got it. And the most prevalent binding for ZeroMQ out there as far as packaging goes is for Python. And that's partly because of us, because salt's written in Python, and we've made everybody package it. But so yeah, you can generally yum install PyZMQ. PyZMQ is just a setup.py. Most of these bindings are pretty easy to install, and they've got all the documentation that you need to get them going. You generally, though, when you've got a binding, you do need to make sure that it is matched, so that when you're compiling it, that you're compiling it to the same version of ZeroMQ itself that you've got installed in the system, or you might run into some unhappy or unpleasant encounters. And yeah, once that's up and running, then you can import it and just go nuts. Yeah. And again, if you guys have something like Fedora going, you can just yum install PyZMQ or apt-get install. Was it libzmq1? I don't know why they have a 1 in there. Because it's version number 2. Does that answer your question?
Yeah, it does.
Okay.
How much of Salt uses ZMQ?
Salt loves the ZeroMQ. Everything this Salt does as far as inter-process communication, and actually, is there a dry erase marker in here anywhere?
There's one stuck to the wall right there.
I think it's time for lights.
Lights.
Because
Lights. Here we go. Everybody.
Blind!
I don't dare erase their.
Yeah,
What?
It's Seth.
That's from
Go
another
ahead.
meeting. That was from what Seth wrote up there.
Okay.
You can blame Seth.
So
The common theme.
Salt's got an interesting topology. So we've got right here a Salt master. And it spins up a rep server right here. And then it spins up another process. So this is all in one box. I'll draw a box around it after I draw these things together. So it spins up another process that is a publisher. Now the publisher for Salt has a hub interface and a pull interface. Okay. And then the master has a, just drew a box for no reason. A router, dealer, ZeroMQ device, and then hooks into, actually, technically, this is more correct. A bunch of request reply workers, and you can have n, a configurable number of those. Okay, and then you've got minions. And these guys are all sub. As well as rec. Now we'll start gluing it together. So, this is running on the master. I've actually omitted a worker process that does cleaning in here, which is why when you spin up a salt master, you go, why are there 5 or 8 processes? It's stuff. It's being a master. Now, so basically, come over here in salt and you say command. You want to run a salt command. That command gets sent via ZeroMQ. So this command sets up a rec right here. Sends that over to the router. It authenticates the command and then sends it forward through a router dealer off to one of these guys, because these are all load balanced workers. This guy then takes that command and builds it into a publication message. So it builds the message, and then it does a push to the publisher process. The publisher process then does a pub out to all of the salt minions. The salt minions are sub, so they gather that information in. They download that message. These messages in salt, we don't do any header checks with these because we make them ridiculously tiny. They all get it and they say, is that for me? We do a quick check. If it isn't, they just ignore it and they go about their business. If it is, then they fire off another process that does work. And in reality, this rec gets created down here. It does work, and then it says, this is the result, and sends it back to this guy, which then goes back to our reply server, or a reply process back here. This guy is then able to communicate back and forth. So for instance, this rec interface here inside of this process can use the file server that is load balanced across all of these guys, or it can use what we call salt pillar, which allows you to create hierarchical and minion data specific sets of information to make determinations. So there's a back and forth communication that can go on between the minions. And so then once it gets back up here on a normal reply that says, I'm just done with my work, so that return message gets back here. This guy gets written out to the file system cache, which by the way is still message packed. Everything's message packed. And then this command has just been waiting for this stuff to show up in the file system cache.
So everything in the red box is message packed.
Everything, every string that leaves process space in salt is a message pack.
How do you push file? I mean, isn't that the push-pull method?
No.
No.
How does the file server work?
Well, no. I mean, like when you push files with salt. I mean, that's going through PubSub.
No.
Okay.
So so there's a tool called Salt Copy that does use PubSub to send out files, which is why there's a big warning in it that says, don't send a DVD ISO on this because that's bad. But it's really good for just publishing some config files. But if you're using Salt States, if you're using Salt Config Management, for instance, all of those files that are going to download are going to go to the Salt file server. How the Salt file server works, because ZeroMQ is stateless. If you look at, say, drill down at how TLS works, or you're drilling down into how a lot of stuff works, you're going to open up a persistent connection and hang on to that connection and do stuff with it. One of the reasons why Beast works to kill TLS 1.0 is because somebody leaves a persistent connection open, and then Beast can decrypt TLS 1.0 because they use an implicit initialization vector, and that can be exploited from other data inside of the encrypted stream, but it's an open connection. Okay, and it's got to be open for like a half hour for that Beast thing to work. So the difference with ZeroMQ is everything is stateless. It's all just one-shot stuff. It doesn't like persistent connections. And so the problem there is that I can't just do a one-shot and load up a gigantic file and then choke it through the line, right? And so how this works is that the minion here sends a little request header that says, okay, I want this file. I'm at location such and such in this file. And it'll start with 0. And then it'll say, and this is where that file is. Shoot that off, and then one of these workers, doesn't matter which, because it's all stateless, says, oh, they just want me to load up what I'm willing to give them from this point in this file forward to until it meets what I'm willing to give them. The default in Salt is a meg. And so it does this. Give me some stuff, and it says, here you go. And then when it replies, it says, this is where I think the file location is. Ending. It confirms. Yeah, I agree. That's where the file location is. And it just goes back and forth over and over again until it has the whole file. And it's actually been surprisingly fast. There's definitely faster file servers out there, but I mean, for doing this sort of rigmarole, it runs really quick. That, and the other thing that's been really nice about it is that since we've already got all this queuing and everything in, I've been able to tell hundreds and thousands of systems, and I just got to spin up a few more workers on the back end and say, hey, just download this file. And I'm sure it takes longer because there's one literal network by it, but Salt doesn't care as far as load or capability on the system. Because it's just able to bring it in and it queues them up and it's happy.
Does this handle like deltas or diffs when you're pushing out files?
It handles strings. So we could very well build more.
You're just not
functionality.
currently doing that though.
Yeah, we could build that in.
That's all I was asking.
Yeah. Yeah, that's on my post 1.0 list.
Some sort of hashing of stuff.
Yeah, I like tracking it, things like that. That's what I was like kind of after.
One of the things that's given us a lot of benefits, though, is that, I mean, inside of Salt, especially for config management, is since we control the file server, and we can add functionality to it. We're not just relying on somebody else's file server. It's allowed us to put some fairly cool stuff in there that allows for mapping out what's available and checking things. And instead of saying, I got to download this file and then find out what its checksum is, like you can just ask the server. You'll say, this is a checksum of that file. Is it different from your checksum? Okay. Then you should download it. So, yeah, a lot of little fun features like that. Any other questions? Geez, I'm way over.